Welcome everyone. In this video lecture, we will solve a GATE 2015 question in which we have to find the conductivity of a piece of silicon. So, in question, it is given a piece of silicon is topped uniformly with phosphorus. So, it is clearly mentioned that silicon is topped with phosphorus. So this one is silicon with topped with phosphorus. So this phosphorus is our pentavalent impurity. So if it is pentavalent impurity, so it will come under N type semiconductor material. Okay. So that thing we have to know, and it is very simple. So for a quick revision, I am just writing N type material is nothing but simply N. So just think about P. So pentavalent impurity. Okay, and this one is our phosphorus. Okay, and if this one is our P type, our impurity will be trivalent impurity, which is our what, boron. Okay, so it is clearly mentioned that there is a N type material because phosphorus is there as a doping. Okay, so this is our case is our N type material in which the doping concentration is 10 to the power 16 per centimeter cube. So this one, the phosphorus having the pentavalent impurity, so this one is nothing but simply we can say the Nd. Okay, Nd. So the Nd value is given, the doping concentration is already given 10 to the power 16 per centimeter cube. Why I am writing N type? Because for the law of mass action, we have to know Np equals to Nis square. Okay. Now for the N type material, now I am telling about the N type. So for the N type, electron is the majority charge carrier and phosphorus is contributing more electron. So this one become the acts as a donor. So instead of N, we have to write as NdP Ni square. So this Nd will be Ni square by P. This one is some theory that we have to know. Okay. And for in this case, again, if we write Np equals to Ni square, now boron is a trivalent impurity. So it will what? Ex- Acceptor. It will accept something. And P type hole is the majority charge carrier. So this should be our P with the whole. So instead of P, we have to write it Na square. So I can write Na equals to Ni square by N. So this one is very important. I am also giving some theory because problem is very simple, but we have to know some basic theory. Np equals to Na square. The equilibrium concentration of electron and hole product is the square of the intrinsic carrier concentration. So this one is also important. Okay, and in our case, this one is our phosphorus one. So Nd is clearly given 10 to the power 16 per centimeter cube because it is doped with the phosphorus. Now, now expected value of mobility versus doping concentration for silicon assuming full dopant ionization is shown below. A curve between the mobility, okay, that is our centimeter square volt per second with respect to doping concentration per centimeter cube graph is given. So we have to find the conductivity of the silicon sample at 300 Kelvin. So this one is the question. So we can easily identify for the doping concentration 10 to power 16, and in our case our material is our n type. So in n type, so electron will be the majority charge carrier, electron will be the majority charge carrier. So we have to think about this curve only, electron curve only. And in this case at 10 to power 16, the value of the mobility is nothing but simply our what, mu n. We can write as mu n as a what, 1200 centimeter square volt per second. Okay, volt per second. So mu n value is also given. So we have to find the value of sigma n, conductivity, okay, in a n type material, because we are just focusing on the n type due to phosphorus, due to phosphorus. Okay, phosphorus. Now a general expression. Now we have to know the general expression for the conductivity in a semiconductor. Conductivity value in a semiconductor, it may be intrinsic or extrinsic, is nothing but simply n q mu n plus p q mu n. This one is the formula. Okay, this one is very important formula. The conductivity of a semiconductor, n, the concentration of electron charge, okay, electronic charge, that is our q, 1.6 into 10 to power minus 19 coulomb. Okay, and mu n, the mobility of the electron, and mobility, sorry, mu n, and it should be mu p, sorry. So mu p is the mobility of hole, q is the charge, and p is the concentration of the, equilibrium concentration of the hole. Okay, so now if in your question we have to think about the n-type material. Okay, this one is a general expression. So we can easily write the expression for the sigma value for n-type, n-type material. So it should be our what, n, n of n, q mu n plus P of n, holes concentration in n-type material, into q into mu p. So this one is the expression for n-type. If this one for the p-type, we have to simply write suffix for n of p, p of p. Okay, I am also writing because this problem is very simple, but we have to know the basics. So that's why I am also giving the np q mu n plus p of p q of mu p. This one for n type, this one for the p type. Okay. So next we have to find this conductivity value. So I am just using the formula for n type. So n type formula, n of n q mu n plus p n q mu p. Okay. So now it is clearly that we are using the n type material. So in n type material, the concentration of electron, that is our nn, or we can easily write this n as a nd. Okay, na, nd. So this ndq mu n plus pnq mu p. So now here we have to take an assumption that the concentration, equilibrium concentration of n is much greater than pn, or we can say simply the nd will be much greater than Pn, because the electron is the majority charge carrier and their concentration, that is equilibrium concentration, is much higher. So this expression can be modified as ndq mu n by replacing these two zero, almost zero, means negligible value we can say. Okay, so this value will be ndq into mu n. Okay, Now we have the value for nd. So nd value will be 10 to power 16. Okay, 10 to power 16 per cubic centimeter. So I am writing, also writing the unit. Now q is nothing but simply 1.6 into 10 to power minus 19 coulomb. So coulomb, I am writing just coulomb. Okay, then we will break everything. Then mu n, the mobility of the electron we have find from this graph. That's why this graph is given 1200 centimeter square volt per second. Okay, per second. So now from here, what we can observe, this centimeter square and this centimeter will be cancelled out. And if we solve this one, we can write 10 to the power 16 into 10 to the power minus 19. It should be our 10 to the power minus 3 into 1.6. Now in the denominator, I am writing centimeter. Okay. Then coulomb. Q is nothing but simply we can write IT. So instead of coulomb, we can write I is our ampere current unit into second. Okay, ampere second. So we can write this coulomb as a ampere into second. Okay, I am just writing because this one is also unit, also plays a major role in any numerical. So that's why I am writing this one as a practice. Okay, coulomb, ampere second. Okay, now it should be our 1200 into volt. Okay, this one is volt per second. Okay, so now what we observe, this second one and second one will be cancelled out. So if we solve this one, here 10 to the minus 3. Okay, and here 1200, and this one is, okay, I am just writing into 1.6 into 1200. Now I am writing all units. So here we can write centimeter inverse ampere by volt. We can write ampere by volt. Okay, now if we remove this decimal point, so it should be, okay, so it should be our 16 into 120 into 10 to the power minus 3. Then we can write centimeter inverse, and ampere by volt is nothing but simply ohm inverse. Just think about V equals to IR. So ampere is there. So 1 by R equals to I by V. So this one is a ampere by volt, that is our ohm inverse. Ohm inverse. So this is ohm inverse, or we can write it Siemens. Now we have to just multiply 16 into 12. So 16 into 10, 160, then it should be 192 into 10 to the minus 3. Then centimeter inverse, or we can write this as a Siemens. Ohm inverse is nothing but simply Siemens. So we can write it as S. Okay, or we can write ohm inverse centimeter inverse. So if we solve this one, if we solve this one, means 10 to the minus 3, 1 2 1 2 3. So it should be 1.92 centimeter inverse Siemens. So this one is the conductivity value. Okay, so this one is a very important question, but we have to know the concept. Okay, and we have to break the unit very carefully, then we can easily identify the answer. Okay, so this is all about this simple question. So I am highlighting the basic. This one is the main formula. Okay, then we have to solve and we have to easily find this one. So the main formula, again I want to write the conductivity. Okay, okay, wait, the main conductivity formula will be our sigma equals to this formula. Okay, better to write this formula, pq mu p. Okay, and one more important formula is there for electron density. J equals to, we can write nq mu n plus p q mu p equals by e. So if we divide j by e, j by e is nothing but simply nq mu n plus pq mu p. Nothing but this one is simply our conductivity. So j, so sigma equals to j by e. This one is also important. This one is current density. Current density divided by electric field. So current density unit, current ampere per unit area centimeter square. Electric field dv by dl volt by centimeter. That is our E. This formula is very important. dv by dl. Okay, so volt by centimeter. So this one will be considered. So it's ampere by volt. So it should be our ohm inverse, centimeter inverse. So these are the very important formula. So at the end we can say the value for this one will be what, 1.92. Okay, 1.92, and because it is in Siemens centimeters, so we have to write Siemens centimeter. So this one is the correct answer for this question. So thank you for watching this video.